Hi guys, and welcome to Mindset Learn Extra. This is grade 10 maths, and tonight's show is brought to you by Liberty. Last week we covered linear and quadratic equations with Natasha, and tonight our topic is linear inequalities, and Dina will be taking us through it. So Dina, well, tell us, what is your lesson going to be about?
Our lesson tonight will look at linear inequalities, specifically how to deal with a negative coefficient, looking at double inequalities as well inequalities with fractions, but all on the linear side.
Fantastic. Okay, so guys, please only make sure you send us questions that are relevant to the topic, and if you stick with us throughout the year, we'll eventually get round to the section you're having difficulty with. Next week, our topic will be trigonometry and triangles. Lots of you have been asking us about our schedule, so if you are in the group, the topic next week is trigonometry and triangles. The show tonight will start off with the lessons on linear inequalities, then after a break we'll work through an example or two. Lastly, we'll be able to tackle your questions on the topic. There are lots of ways to get hold of us. You can get hold of us on our Facebook page, and it's facebook.com/learn extra. We're also on Twitter @learnextra. So while you're watching, shoot questions off to us and we'll get round to them in the third part of the show. I have another Casio calculator to give away tonight to one of the best questions posted on Facebook. We will be announcing the winner tomorrow on the page. After the break, we'll be back with Dina.
See you now. Welcome back, everyone. It is linear inequalities, and if you're in grade 10, you're about to find a brand new topic. But if you're watching us and you're in grade 11 or 12, then I've posted up a question, a challenge question, so that those of you who'd like to just attempt some real challenging maths can get to it. So the question is also being posted on the Facebook page, so please have a look and you can follow us there as well. Right, we're going straight into some theory, and I'd like to take us into what I'm going to look at. Okay, let's go onto the page. There we go. Right, I'm going to look at what is the meaning of the inequality sign, and you would have seen this in grade 9 or even before that, and I'd like to look at two versions of writing a list of numbers. The first one being set builder notation. So we could, what happened to my page? Okay, sorry. Here you go. Okay. Set builder notation or interval notation. That's the two ways of being able to write a list of numbers. So the first one would be x, just get a pen, if x is greater than or equal to 3, then what we are saying is that the list of numbers will start at 3 because it's inclusive of 3, and it will go 4, 5, 6, etc. We could also have, for example, x greater than 3, in which case we're only looking for the numbers that are greater than 3, not including 3, so we would exclude it. We could also look at if it's natural numbers or real numbers, and if it was natural numbers we would start from 4, 5, 6, but if it's real numbers we would have all the rationals and irrationals between 3 and 4. What does this look like in an interval notation? Well, the first one would be that x is an element of the numbers from 3 to infinity, and the second one, the numbers from 3 to infinity, but excluding the value of 3. And this is assuming, interval notation, that the numbers are real. So we don't write naturals in interval notation, we would only write real numbers in interval notation. So just to go through it again, if the number is included in the set, then we would have an equal sign and a square bracket to indicate that it's inclusive. If there's no bar, then we're excluding the 3, so we then have a 3 on with a round bracket. Now, we would also get the number line version. So if we were trying to sketch greater than 3 or equal to 3, I'm just going to include 3, 4, and 2 on my number line, and this is the set of real numbers. Then if we had, let's say we had this set of numbers, it's including 3, so we would have a colored in circle with an arrow indicating that it's greater than 3. If it's the set where it's excluding 3, then we'd have an open circle to indicate that it's greater than 3. So it would increase towards infinity but the open or the closed circle indicate whether we are including that value or excluding it. So that's a little bit of theory that you've covered before and that we're going to utilize in our next section. Right, let's see what solving an inequality is all about. So if we had solve for x in the inequality 4x minus 1 is greater than 11, let's make it equal to 11, then how would we go about solving for x? Well, the first thing that we did when we solved an equation, because that's the only other scenario that we've dealt with before, is that we would extract the variable from one or the other, one or the left or the right of the equation. And so if that's where the variable is, we'd like to get rid of this negative 1. So we would have 4x is greater than or equal to 12 by adding 1 on both sides. And now if we're wanting to solve for x, we would divide by 4 on both sides. So we would get this relationship for x and the inequality. X then is greater than or equal to 3. So what we're trying to say is find an x value so that find an x value so that 4x minus 1 will always be greater than or equal to 11, which is the same thing as saying when is 4x greater than or equal to 12. And we're saying that for every x that is greater than or equal to 3, and we're assuming here that x is the set of real numbers, then we are going to have infinite amount of values that will satisfy that inequality. And that is a mathematical terminology, that the x values you find will satisfy the original statement, which in this case is an inequality. Right, so that's, I think, quite straightforward. And then you'll also be able to work out on the number line when x is greater than 3. What I'm curious this afternoon to look at is what happens if you have negative 4x is greater than or equal to 12. Then what is the x value? So if we divide by negative 4 on both sides, we would get x is greater than or equal to negative 3. And my question is that possible? If x is greater than negative 3, will it give us a valid statement? Now think of a number that is greater than negative 3. Negative 2, for example, satisfies that. Let's now substitute back into the inequality and see whether we get a true statement. Negative 4 times negative 2 is 8, and 8 is not greater than 12. So there is a problem with this statement. It is not true. Okay. And I want to get into another page so we can just work out what is happening over here. If I say that 2 is greater than 1, then if we perform all the primary operations on here, if I add 2 onto the right and I add 2 onto the right, then is 4 still greater than 3? Is that still a true statement? Absolutely. If I multiply, and let's just get back to the original. If I have 2 is greater than 1, and if I multiply by negative 2 on both sides, what do you get? A negative 4, and on this side I get a negative 2. And the question is negative 4 still bigger than negative 2? And the answer is obvious, no, it's not true. So whenever we're multiplying by a negative number, we will have to reverse the inequality in order for the statement that you've just written down to still remain true. So the truth is only going to happen if that inequality is reversed. So notice when we added to both sides, there was no need for that reversal of the inequality sign. However, when we multiply by that negative, it will have to happen in order for it to remain true. So there is the same thing. Let's just have a look at what happens with a division. If 2 is greater than 1, then if we divide by negative 2 on the left and we divide by negative 2 on the right, then we have 2 divided by negative 2 is a negative 1, and 1 divided by negative 2 is negative a half. Is negative 1 greater than negative 1, negative a half? No, negative 1 is smaller. So in order for it to remain true, I also have to change the inequality. So it only happens if we have a division by negative 2 or a multiplication by -2. So any product or quotient with a negative integer will require us to reverse that inequality. So if we go back to our question where we saw that contradiction, go right back. I think it was on that page. Okay, I've lost the page now. Let's just go down. Okay, it's not coming down. Okay, I've lost the page. Let's just go on to a new page. So when we looked at earlier at -4x being greater than 12, and we got that x is greater than 3, there was a problem because the value didn't satisfy it. Now we know that what needs to happen is that when we divide by -4 on both sides, at the stage when we're dividing, this has to change. So that has to be smaller than -3. So if we now look on the left here, -4x and greater than 12, which values will make that true? We say anything smaller than -3 will satisfy this inequality. So a -4, for example, times a -4 will give me 16, and 16 is bigger than 12. So therefore, it satisfies that inequality. So this set is the solution set for that. Now, oftentimes, you'll be asked to give that solution set in a particular format, set builder notation, interval notation, or number line. If we had to put this x is smaller than -3 on the number line, you need to give at least 3 values. So you'd have a -3, you'd have a -2, and you'd have a -4 and a -5. And we're asking for the x to be smaller than, so you need to read values to the left. And if we just color-coded that, it's not including -3. So -3 is not the value we want to start off with. So we will have an open circle, and then we will be reading to the left of -3, so all the values that are smaller than -3. If this included -3, then we would have closed that. So either you need to look at, does it include the value or exclude the value? And here we are saying that x has to be a real number. Because if x was a natural number, let's say x was not a real number, if x was a natural number, then there would be no values for the set because they're negative. If x is an integer, then the way that you would capture those integer values would be to, it doesn't include -3, so it would include 4, it would include -5, and you'd carry on to infinity. So you'd have discrete values, -3, -4, -5. But because they're real numbers, we're saying that this line is telling us that every single number between -3 and -4 is included in that set. And if we had to plot every single number infinite amount of times, then we would get a line that would join those points, because those points would be so close together. Right, so that is really the theory behind the inequalities, is to be able to understand what the sign means: smaller than, greater than, smaller and equal to, greater than and equal to. There are 4 of them. And then to be able to work with variables in the context of whether those variables can be smaller than or greater than. And then just to be able to work with a linear inequality means that the power is 1, and to be able to solve for that when the coefficient of the variable is negative. And if the coefficient is negative and we're dividing or multiplying, then that inequality will reverse. And that is something that's brand new to grade 10, and I'm hoping that you've grasped that, because when you come back from the break, I'm going to look at what happens when you've got a double set of inequalities and what happens when we've got fractions as well. So let's go to an ad break.
Hi guys, and welcome back to Mindset Learn Extra Live Maths for grade 10s. Hope you're all having a fantastic show. I just wanted to make sure that you guys know that we have posted the challenge question on the Facebook page, and that's www.facebook.com/learnextra. You can also chat to me, Indiana, on Twitter @LearnExtra. We are also, guys, on PepText, which is quite great. The group code is Mindset, and the way you download that is that you go to www.peptext.mobi on your cell phones, and that's www.peptext.mobi, and that's for PepText, and the group code is Mindset. And what we're going to do is we're going to go straight back to Dina and get those questions in, and I hope you're having a great show. Dina, are you ready for us?
Ready. Right, everybody, welcome back. Let's just go over what we did a little while back. We said 3x is greater than 21, how to solve for x. X is greater than 7, no problems, no reversal of inequality. However, when a coefficient is negative, we're going to have to reverse the inequality in order to make that statement true. So that's what's going to happen. Okay, so that's what we did before the break. Let's go into a double inequality, and let's see what a double inequality looks like first of all. You'll be asked to solve for x in this question, and if you look at it, it's got the variable in the middle and it's sandwiched between two limits, between -1 and 8. And how do you read this? Whenever there's a double inequality, you read from the middle out. So 2 minus 3x must be smaller than or equal to 8, and you'll also read it from the middle to the left. So 2 minus 3x must be greater than or equal to -1. So that's how you'd be reading that inequality. Now, to solve for it, you solve in exactly the same way as before. You would treat the constants first, and then you would deal with the coefficients second. And instead of just doing it to one side, you wouldn't just be using the additive inverse or the inverse operation on one side. You'll actually have to work on both sides simultaneously. So this is quite a nice balancing act, working both on the left, in the middle, and on the right in order to solve for that variable. So let's see what it looks like. It's useful to use some color so that you can see that you're doing it in all cases, and what we want to do is to be able to get rid of this 2 because we're trying to solve for the variable. So we need to minus 2 in the middle, we need to minus 2 on the left, and we need to minus 2 on the right. And after performing those operations on all three sides, we now get a minus 3 is smaller than or equal to negative 3x, and on the right hand side 8 minus 2 is 6. And now we're going to divide by -3. I'm going to use a different color to show that I'm going to divide by -3 everywhere. And whenever there's an inequality and we're dividing by a negative number, we need to remember to reverse the inequalities. Otherwise, the statement's not going to be true. So the changing of the inequality is going to mean that dividing by -3 here, I'm going to get an x. But now, I'm going to divide left and right, so that's going to change direction, and that's going to change direction. So that was less than, it's going to become greater than, that was less than, that's going to become greater than. And we are dividing by -3, so let's just get that back, there we go. -3 divided by -3 is 1, and then 6 divided by -3 is 2. So going over that again, a division by -3 has to happen on the left, in the middle, and on the right. Starting in the middle, because that's what x is, you'd get a -3 divided by -3 is a 1. We've reversed the inequalities in both places, and then we're dividing on the left by -3 and on the right by -3. So we now have that, and let's just fix this -3 here, because that should be a negative. There we go, that's better. So we now have that x must be smaller than 1, and x must be greater than -2. Now, how would this look like on a number line? And before we get there, you must just remember that from the left to the right, it reads correctly. So 1 is greater than -2. If this was a -3, and -3 was greater than -2, there was a problem, this would have been incorrect. So the order that you're reading must make sense numerically as well. The number that's there will be true for 1 being greater than -2. Right, what would our number line look like? Let me see if I can get a straight line. Okay, let's rather go there. Here's my number line, and I would need a -2 on the left, -1, 0, 1, and 2. And reading this way, x must be greater than, and it's equal to as well. So what must happen at -2? must be colored in. And then we must have that x, reading that way, is smaller than and also equal to, so it must be colored in. Okay. And if we now join them, we are saying that every number, let me see if I can get a nice pen here. There we go. So every number looks like a little hot dog. Every number between -2 and I've gone too far. Shouldn't have gone out all that way. Let's just undo that. We should actually only go up to 1. There we go. Just to fix that. There we go. So we now finish off at, don't know why I'm going to 2, but anyway, there we go. So every number between -2 and 1 would satisfy the set. Now let's try a 0, for example. If we tried 0 in here, we would get that -1 is smaller than 2, which is true, which is smaller than 8, which is true. If we tried a -1 in here, -3 times -1 would be a 3 times a 2 is a 5. So we get -1 is smaller than 5, which is smaller than 8. So you could test all these values between, I think it was that one, between -2 and 1, and they would match that. And your number line would be almost like a dumbbell having 2 little bells on the end and then that little straight line to indicate that set of values. Okay, so that would be a double inequality. What about a fraction? Because our challenge question was a fraction. How would you deal with fractions? Okay, and I've got an example as a fraction. X minus 7 over 3 must be greater than 6x. Actually, let's just do that. Get rid of that. And let's say 2x minus 4 over 2. Okay, so there's a fractional one. Okay, the first thing that you need to do is to say, well, these denominators are going to be problematic. They're in the way. So what do you do with denominators? Like you've done with equations, you will get a common denominator. So my common denominator would be 6 for 3 and 2. And then we would find the equivalent fractions for the 3 and the 2. This needs a 2, so that needs to be multiplied by 2, which is 2x minus 14. And on this side, you need a 3, so you'd get a 6x minus a 12. Now, because you've got the same denominator on both sides, we can multiply by 6. And so we now just compare the numerator 2x minus 14 and 6x minus 12. And that's now linear. It's not a double inequality. And you can now tackle it. So 2 minus 6 is negative 4. And that must be greater than negative 12 plus 14, which is 2. And what happens now? You've got a negative 4 that you're dividing by. So a negative will always reverse the inequality. Dividing by negative 4 will give us x. Reverse the inequality, must be smaller than 2 divided by negative 4 is negative a half. Okay, so any number that's smaller than negative a half would satisfy that equation. Let's test. If x is negative 1, for example, that would give me a negative 2, negative 14, which is negative 16 over 6. My pen doesn't like working on that side. Okay. And this one would give us a negative, well, let's go to the original. Makes it easier. Here's the original. So if we took negative 1, we said, or negative 2 makes it even easier. Negative 2 minus 7 would be negative 9 divided by 3 would be negative 3. And then we'd have on this side negative 4 minus 4 is a negative 8 divided by 2 is a negative 4. And the question is negative 3 greater than negative 4? And it is. So our set actually works. And that's what you must get into the habit of. It's always testing that your equations or inequalities, the solutions that you get actually make sense in the original. It makes for quite confident work once you can prove to yourself that what you were doing was actually correct. So that's a double inequality and fractions. And over to Indy.
Hi guys, what we're going to do is we're going to take a quick break. Please get your questions in for Dina. We are taking them in the last 10 minutes of the show. Don't forget that a Casio calculator is up for grabs. So as many comments as you can, it doesn't matter what it's about. And just remember, there's no such thing as a silly question, guys. Really. So what we're going to do, take a quick break and we'll see you now. Hi guys, and welcome back to Mindset Learn Extra. This is grade 10 maths, and I hope you're all having a fab time. I know a whole bunch of you have answered our challenge question, and I see Dina, there are a few that have got it right, and there are a few that have got it wrong. But guys, don't forget that if you got it wrong, that's okay as well, as long as you learn from the mistake. I think what we're going to do is we're going to go to Dina so she can recap the question, and then we'll work over it together. What do you think, Dina?
Great. Thanks, Indy. Let's have a look at the question again. And I just want you to work with me on this question. It has some fractions in it, and it's got some interesting algebra. And if you got an answer of A is equal to -7, that's not right. If A is greater than -7, that's not right either. So let's really have a look at what the answer actually is. Right, the question's up here on the board. 1 minus A over 2 minus 2 minus A over 3 is greater than or equal to 1. What do we do when we have fractions? We've got to find a common denominator. So let's do that. We've got a 6 that we're going to work with. But before we multiply by 6 on both sides, let's see what the fractions look like as 6. This fraction needs a 3, so we're going to multiply the 1 minus A by 3. And this fraction here needs a 2, so it's minus 2 into 2 minus A, and that's greater than or equal to 6. 6 over 6 is 1. Now that the denominators are the same, we are going to multiply on both sides by 6, and so what are we left with? We're left with 3. Don't forget that it's a binomial, so each term gets multiplied by the 3. And then we're going to multiply by -2. So we get a -4, and we're multiplying by -A, so it's a positive 2A, and all that must be greater than or equal to 6. So the common denominator has been sorted, the equivalent numerators have been dealt with, so now all that rests is for us to collect the x terms and the constants and see what is that coefficient doing, because remember, if that coefficient is negative, something is going to happen. So we have a -3 and a 2, which is a -A, and we've got a 3 minus a 4, which is a -1, is greater than or equal to 6. So we've got a -A is greater than or equal to 7. At this stage, we've got -A, and we said earlier that if the coefficient is negative, that inequality has to change direction, otherwise that statement will not be true in the end. So A is going to have to be, let's just go down a bit, there we go, A must be smaller than or equal to, changes direction to -7. What does that look like on a number line? It would have a -6, -7, -8, so those are my x values. At -7, I'm going to have a colored circle, closed circle, and then it's going to be red to the left to show that it's got to be smaller than -7. So for everyone that got A smaller than -7, well done. Your algebra is very accurate. Really proud of you. Well done. Back to you, Indy.
Well done, guys. You guys have done brilliantly as usual. Valentine, Anele, I wanted to wave, and Sylvester. Everyone's been tuning in, grade 10s. I was wondering where everyone was, and they clearly are on the page. So well done to you guys that did get it right. If you didn't get it right, it's okay as well. Practice makes perfect. I think, Dina, what we're going to do is we're going to go over another question, or shall we go to a break? Should we go to a break? Okay, we're calling for a break. We'll see you now in 2 seconds. Don't forget to keep those questions coming, guys. See you now. Hi guys, and welcome back. Guys, I'm loving that you're all helping each other out on the page. I love Kashifa, that you've been helping out, and guys, you've been working through these problems together. I think, that's exactly what it takes. It takes all of you guys working on the Facebook page to solve something, and it's much easier. That's how you teach yourself, is by teaching others. So while we were sitting during the break, we spoke to Dina and we said, can we give the mindsetters a harder question? Which Dina said that she'll be doing a bit later. So what we're going to do is we're going to go straight to Dina. Guys, don't forget to put your questions on the page because we will be going over them in the last 10 minutes of the show. Without further ado, over to you, Dina.
Thanks, Indy. We had a question about why you reverse the inequality, and I just want to go over the natural numbers. Whenever you're asking those questions, give yourself some numerical examples to really grasp what is actually happening. Let me go over the multiplication of a positive number. If I multiply by 2 on the left and the right, we get a 4 and we get a 2. In order for us to compare the 4 and the 2, what inequality would you place between the 4 and the 2 in order to make it true? Would you put a less than sign or would you put a greater than sign? Because you've only got those two as options. And it's obvious what we would put in there. We would take the 4 and we would say 4 is greater than 2. So the inequality was greater than, it remained greater than. The comparison between 4 and 2 is exactly the same as the comparison between 2 and 1. They are both numbers on the left are greater than the numbers on the right. So nothing has changed. If we look at 2 greater than 1 and we now multiply by a negative 2, if we multiply by negative 2 now, we're now going to get a negative 4 and we're going to get a negative 2. 2 was definitely greater than 1. What is the comparison between negative 4 and negative 2? How do we compare that negative 4 and negative 2? Is negative 4 smaller or is negative 4 greater than negative 2? And on the number line, it's obvious. Negative 4 is smaller than negative 2. So what has happened is that this inequality has changed in order to make that comparison true. And that comparison will only change, that inequality will only change when you are multiplying by a negative. So we've got negative 4 is now smaller than. So we've got that statement here. So multiplying by a positive, nothing will happen. Multiplying by a negative, it will take place. And I think that in the previous question, we got to this statement. In the challenge question, we got the following. We got negative a was greater than or equal to 7. And a lot of you said a was greater than or equal to negative 7. But remember that this coefficient is negative. So with a negative coefficient, you're now going to divide by negative 1. And if you divide by negative 1, the first thing you'll address is that this inequality, in order for it to remain true, will have to change. So that a is now is less than or equal to negative 7. So even though a lot of you got to 7, you said negative. It cannot be, you said negative 7, it cannot just be negative 7 because it's an inequality statement. So we're saying it's every number that is smaller than or equal to negative 7. That was the explanation that some of you were querying. And then for a more challenging one, in grade 10, that's as challenging as it gets, but let's give you maybe a double inequality with a fraction. How's that? So if I gave you a double inequality, we'd go 2 minus 3x over negative 1. And let's set a double inequality, so greater than 0 and smaller than or equal to, let's make it 10. And let's see what you come up with. Shall we do the question together?
Yeah, I think that's a great idea.
Okay.
Yeah.
Right, so you wanted a more difficult one. Here it is. Why? It's not more difficult in the sense that there's something lurking behind there that's making it so hard. It really is the complexity, the fact that there are layers that you need to get through in order to get to x. So the layers kind of hide how easy it actually is. So everything in maths is easy, unfortunately. So don't get out there and begin to believe that this stuff can be complicated and difficult and that kind of thing. It isn't. It really is very simple, but we need to unlayer it. So let's do that. So the first thing we would deal with is this negative 1 because it's a fraction. And if we multiply by negative 1 on every side, what is negative 1 times 0? It would be 0. But the moment we do that, this inequality sign is going to change. So we're now going to be left with 2 minus 3x is also going to reverse, is greater than or equal to negative 10. Okay, so we just need to undo that. Minus 3x is greater than or equal to negative 10. Okay, now we've got a constant and we've got a coefficient. So we're going to get rid of the constant first. Minus 2 on the left is less than or equal to. We're subtracting, we're not multiplying or dividing, so the sign doesn't change. Minus 3x is greater than or equal to minus 10 minus 2 is minus 12. And then we're now going to get rid of the negative 3. So we're now going to divide by negative 3. Dividing by negative 3 across an inequality is going to do what? It's going to reverse it. So we're going to have less than or equal to 2/3 is smaller than or equal to x. And this one's also going to reverse. So it's smaller than or equal to 4. So the x value, and to make it interesting, let us just come down here a bit. Okay, right, so we just lost that. It's smaller than or equal to 4. Smaller than 4, and it was greater than 2/3. Would be, let's say this was equal to, what would this look like on a number line if x was natural? Or if x was an integer? Then if x was an integer, you'd have to start with the first integer after 2/3, which would be the integer 1. And then you'd have a 2, 3, and a 4. So your number line would have the number 1, the number 2, the number 3, the number 4. There would only be 4 values that would satisfy that. But if x was real, if you had real numbers, then you would have 2/3 and 4, and you'd be sitting between 2/3 and 4, and in that case, you'd have the set of real numbers on your number line. My pen's not really colouring in, but there we go, because it's inclusive of those. If it excluded those values, then you'd have that open circle. Okay. Right, so that's as challenging as it gets, those little layers of denominators, constants, coefficients, all in the end to try and extract that x value. Indeed, let's see what the callers are saying.
Okay, let's have a look here. Somebody wants to know here, this is Katiwe. Katiwe wants to know, why do the signs keep changing? But we've just gone over that, right?
Yeah, we've just done that.
Yes,
yeah.
we've just done that. Guys, what I want to ask you now, before Dina continues, if you can please send us questions and show me where you're getting stuck and what you're not understanding exactly. It will help Dina to get through it a lot faster, right? Okay, so I think maybe what we're going to do is move on to more examples. If you do get stuck, let me know on the page and I'll stop Dina as we're going through it. Fantastic. Thanks, Dina. So take it away.
More examples.
More examples.
Okay, more examples.
Yeah, more examples.
Okay, let's just go back to the one where the question was, why do the signs keep changing? And I guess it's the question, they must be more specific when they actually talk to us, because is it the example we've just done? Is it some example that they're doing?
Exactly,
students are doing, etc. So let's just look at here. The sign had to change when we multiplied by a negative 1. So it changes. When we added negative 2, you'll notice the sign stayed the same. All of a sudden, in this step here, we're dividing by negative 3. So we have the sign changing with the division of negative 3. We've got the sign changing with the multiplication of negative 1. So the operations that involve either, we don't have any highlighters, there we go. Either the product, okay, it doesn't do, okay. Right, so either the product or the division. Let's just write that at the end. So just to summarize it. Multiplying or dividing by a negative. Those are the only two times that you will get the reversal of that inequality. So in the example that I've just done with you, when we were multiplying by -1 and we divided by -3, both those operations will carry with it that change of inequality. So multiplying, dividing by negative is the only time that that sign has to change in order to maintain the truth of that inequality.
Okay,
Any
fantastic.
further questions?
Okay, we do have one. I think here. Wait, where is it? This one's from Wendy Seeley, and Wendy Seeley wants to know what would happen if we're working with a squared number.
Ah, very good. A squared number. Let's
A
just
squiggly number.
Yeah, I heard. Okay, so here's something more challenging for those of you who are looking for something really challenging. What happens if now x is squared and not just x greater than 4? For that, I'm going to suggest that we actually use a table of values to see what's happening, because it's very interesting what happens. Let's say x is 0, for example. 2, 3. And let's go -1, -2, and -3. If x is 0, then 0 squared would be 0. So if I took x squared values over here, and these are my x values. If x is 1, then x squared would be 1. If x is 2, then x squared would be 4. If x is 3, then x squared would be 9. What happens to the left of 0? X squared would be 1, x squared would be 4, and x squared would be 9. And the question is, when is x squared greater than 4? So we can see, we can extract that anything greater than 4 would be anything that's bigger than 2 and going that way. And anything smaller than -2 would also give me true values. Now, as a grade 10, I think we, even here on Learn Extra, we haven't yet covered graphs. And when we cover the graphs, you'll be able to get a bit better grasp on this. But for now, if you draw a table of values on the function, on the squared function that you've been asked, you'll be able to say the x squared bigger than 4 will actually be anything greater than 2. So if x was greater than 2, or it's a split set, you have an x smaller than -2. So you actually get two sets. If we had an x squared smaller than 4, then that would obviously be the numbers between -2 and 2, and this would be the set where x was smaller than 2 and greater than -2. And this we call a split set, and this set has actually got the limits on the double inequality. So a squared number you actually have to do very differently. You've got to propose a kind of a different method, because it gives you usually those two sets of values. So that is really into the grade 11 scope, but it's good to know. I like those questions. What happens if it's not linear? What happens if it's quadratic? And what happens if it's cubic? But like I say, once you've done graphs, you'll be able to actually use a graph to show you how we actually read those values as well. So for now, as long as you're just plotting by trial and error, that should be sufficient to cure your curiosity. Any other questions?
Okay, guys, send me through any questions things that you don't understand. We do have a question where somebody's given us something to work out, but I mean, we would prefer that you show us where you're not understanding something as opposed to redoing something. So, if you want to tackle a question, Dina, we can do that as well.
Let's do that.
Okay, let's have a look. Let's see, give me 2 seconds. Okay, so this one's from Anugrah, and he says, could you help me with this? Solve x minus 1 equals 42 divided by x.
Solving for x.
Yes.
Okay. Right, do you see what the student has given us is an equation. It's not really an inequality. So it's going to turn into a quadratic equation, which I know that you did last week. So let's treat it as an equation and then see if we can transform it in some way into an inequality. Okay. Right. The possible problem that we have is there is this denominator. Okay. So to get rid of any denominator, we multiply on both sides by that denominator. So we're going to multiply on the left by x, and we're going to multiply on the right by x. So we've got 42 over x times x. And now what happens is we've got a product on the left that's x squared minus x, and we've got a product on the right that this x goes in there, and we're left with 42. To solve that equation, we've got x squared minus x minus 42 is equal to 0. And to solve that quadratic, we've got x minus 6. Actually, if we just say there, we've got x minus 7 and x times 6 equals 0. So we've got negative 7 plus 6 is negative 1, and negative 7 times 6 is negative 42. So we've got x minus, or x equals 7, or x equals negative 6. That is what an equation does. It gets you to finite values in your equation set. Said earlier, let's see if we could transform this into an inequality. We're then transforming it into a quadratic inequality, which wasn't really the scope of our lesson today. But let's see what it looks like if we were trying to solve for x in inequality. And we had x, what was the equation? X minus 1 equals 42 over x, eh?
Yes.
So we can just undo here. Let's see, let's just put in an inequality, and let's make it smaller than. When would x minus 1, so we formulated a new question, okay? And it would, all those things would happen, except we would get here to this step here, and we would get x squared minus x minus 42 is now going to be less than 0. Which would give us these factors, x minus 7, exactly the same thing, but in place of the equal sign, we would have is negative. Okay? So going down, we're now saying, when is the product of x minus 7 and x plus 6? When is it negative? And we saw earlier that it is equal to 0 when x is 7 and x equals minus 6. So our question is, what is happening between, okay, so at negative 7, we've got a 0, and we've got a 0. What is happening between negative 7 and 6? Well, between negative 7 and 6, we've got a 0, for example, okay? So if we substitute naught in, we've got negative 7, and we've got a 6, which gives us a negative product. And if it's bigger than 6, let's make it 10, then we've got a 16 over here, and we've got a 3. So it's going to be a positive product on that side. And to the left, we would have a, let's say, negative 10, which would give us a negative 17 here, and a negative 4. So it would give us a positive product. Therefore, when is that product negative would really be between these values here. So it would be between negative 7 and 6. And we've got, it exclude those values, so x could be between that set of values. So as you can see, for any inequality, for any equation, we could turn it into an inequality, and instead of finding finite values, we could actually find a set of infinite values. And that is all from Inequalities. Over to you, Indy.
Fantastic. Thank you so much, Dina, for such a fantastic lesson. And guys, I loved the way that you all tried to help Anugrah on the page. I see Kashifa and Abel, you tried to actually work out the equation, even though it was not an inequality, which I think is really, really cool. I just want to say big up and big thanks to Liberty again for allowing us to host this awesome show. And grade 10s, thank you so much. Our time is over. We will be back, same time, same place. Grade 11s, don't forget that you're next. Thank you so much for a great show. See you next week, same time, same place. Bye.